Hey everybody, so today we're going to talk about momentum and impulse, two very important concepts here at the end of Newtonian physics. Newtonian physics being the study of forces and basic motion. After we get through chapter 11, which you learned a little about already through the note-taking assignment, we're going to move on to heat, thermodynamics. Okay, so anyways, today, momentum and impulse. We're going to go through it somewhat quickly because you've already taken some notes on some of this, but I want to make sure everybody's got the basics of this bit of information down. Okay, moving on. So, first of all, how the word momentum is used every day. Then you think of an example. How is the physics definition of the word different from the everyday usage of the word? So, it's about time of year for the football playoffs. Okay, if you've been watching any football, I watch a ton of football. It's all about who has momentum right now. And the everyday usage of the word, we talk about things like a football team or sports team that's doing really well. They've won the last few games by a lot. They've got a lot of momentum, meaning they're hard to beat or hard to stop. And believe it or not, that definition is not totally different from how we would use it in physics. Okay, as you learned yesterday, that definition of momentum in physics has to do with a resistance to change, a persistence of motion is how the book describes it. Okay, so think about this example. If I have a 1 kilogram sphere that is traveling at 100 meters per second and a 100 kilogram sphere moving at 1 meter per second, which object do you think is going to have, or if you're trying to stop them, I should say, which one do you think will stop first? So if you apply the same amount of force to stop them, which one do you think is going to be easier to stop? Do you think it's going to be the big object or the little object that's easier to stop? Well, if you consider your options about it being the big object or the small object, the difference in velocity actually makes it to where it's a tie. It's actually going to be an equal difficulty to stop the two objects, the little one moving fast or the big one moving slow. So now why is that? Why is that true? Well, when we look at the actual definition of momentum, that's P. It's actually a Greek letter rho, R-H-O, but we'll say P, equals mv. Now, P is momentum. The original definition of the word include the word persistence of motion. That's where the P comes from. Persistence of motion equals mass times velocity. Panthers equals Medina Valley. So mass times velocity. These are two concepts we've gone over a lot before. Okay, so P equals mv. When you look at the multiplication of the two, you'll notice that the two spheres have the same momentum because 100 times 1 is the same as 1 times 100. Okay, and the unit of momentum, so it doesn't really show it here, but take a look at what's written on the screen here. Mass is kilograms, velocity is meters per second, so your units of momentum is literally kilogram meters per second. That's how you say the unit. So this momentum is measured in kilogram meters per second, has a momentum of 100 kilogram meters per second. So I like to call momentum as stubbornness. Which one is going to be more stubborn, more difficult to change how it's moving? So, more practice. A red truck and a blue truck have the same mass. The red truck is parked and the blue truck is traveling along the highway at 60 miles per hour. Do both trucks have inertia? Do both trucks have momentum? So this is a big concept, is the connection between inertia and momentum. Now, inertia we went over as Newton's first law of motion. Newton's first law of motion is known as the law of inertia. Inertia, I also talked about stubbornness, but stubbornness to change any state of motion. The first law of motion says that an object at rest remains at rest, an object in motion remains in motion unless acted upon by an outside force or an unbalanced force. So inertia applies to things that are sitting still and moving. Another definition of momentum, I say, is it's inertia in motion. It is inertia, but only in motion. If it's sitting still, then velocity is zero, and anything multiplied by zero is zero. Okay, so in order to have momentum, you must be moving. In order to have momentum, you must be moving. It's a requirement. Okay, so thinking about this example, do both trucks have inertia? Inertia is a property of matter. If it's moving or not moving, it doesn't matter. They all have inertia. They all resist changing their state of motion. It's going to be hard to stop the truck that's moving, and it's going to be hard to start moving the truck that's not moving. Now, do both have momentum? Are both moving? That's the first question. Are both moving? No. The blue truck has momentum, and the red truck does not have any momentum because it's not moving. Momentum is sometimes referred to, like I just said, as inertia in motion. Inertia in motion. Okay? Awesome. We just talked about how the units of momentum are kilogram meters per second. Okay? Because you've got kilograms times meters per second. Kilogram meters per second, units of momentum. This is honestly a really straightforward concept. How do you get more momentum? More mass or more velocity? That's it. It's the only way to get more momentum. More mass or more velocity. Okay, so we'll do some practice here together, but this is a pretty straightforward concept. If the momentum of what is the momentum of a 60 kilogram sprinter running at 7 meters per second? Well, we know that the mass is 60 and the velocity is 7. Momentum is mass times velocity. 60 times 7 is 420 kilogram meters per second. Now, what is the velocity of the same sprinter if her momentum is 270? Well, the mass isn't going to change, so we could divide the momentum by 60, by the mass, to figure out that her velocity was 4.5 meters per second. And it's a straight connection to know that if you want to double momentum, you would double velocity. Okay, so momentum is pretty simple. We'll do one or two more questions. A 2,000 kilogram car and a 4,000 kilogram truck are both traveling at 10 meters per second when they hit a wall. Which has more momentum before impact? We'll take a look. You can do the math, but think about it this way. Same velocity, so the big difference is what? Mass. Which one's going to be harder to stop? The heavy one or the lighter one? Well, hopefully you figured out that it's the truck, the big, heavy 4,000 kilogram truck. Okay. Now, the ratio of their momentum is a little different. Okay, you actually have to find the numbers and know that the big truck is twice as much as the little truck, so the ratio is 2 to 1. 2 to 1. It's a fraction. It's twice as much. That's all it's asking. Okay? And last question we'll do together. A boulder is dropped from rest and hits the ground at a speed of 15 meters per second, transferring 1,200 kilogram meters per second of momentum to the earth because it's sending energy. So it sends that much momentum to the earth. Think of impact. What's its mass? So what are we being given? Momentum and velocity. Plug it in as you see here. Momentum is 1,200. Velocity is 15. To solve for mass, we would divide by 15. 1,200 divided by 15, 8 kilograms. Okay, and that's the basics of momentum. Let's talk a little about impulse. Okay, so we'll talk a little about impulse. Oh, I did want to mention one last thing. One last little bit. First of all, super important, momentum is a vector. It has a direction to it. You may have noticed in the textbook there were little arrows over the P or the rho in the book, and the V as well. That just says that that variable is a vector. So momentum is a vector. For one-dimensional motion, meaning just one line, this means that the direction of motion determines the sign of momentum. So if it's moving in the positive direction, that way, then it's got a positive momentum. If it's moving in the negative direction, then it has a negative momentum. Okay? As you can see there. Now, when we talk about a system, total momentum of a system being a whole group of objects, if I wanted to know what the total momentum of this system is, you have to take everything into account, which means both momentums that are present. Okay? So if you have positive 100 and negative 100, what do you think the overall momentum is of the whole system? 0. Okay, because they cancel out. Positive and negative here cancel out. Total momentum of a system is about to be super important next week when we talk about conservation of momentum, which you wrote a little bit about in your notes. All right. Now we'll talk about impulse. Pull that up real quick. Yep, that's still momentum. There it is. Aha. Got it. Okay, impulse, directly connected to the concept of momentum, like we talked about yesterday, or in your notes worksheet. Momentum of an object changes as it speeds up or slows down. Okay, so you could find an object's change in momentum if you wanted to. Remember the delta, that's the triangle, means change in, and it means final minus initial. So change in momentum is final momentum minus initial. So for example, if I want to find the change in momentum of a 2,000 kilogram car that slows to a stop and loses all of its momentum, you could figure out what it starts at, 2,000 kilograms going at 10 meters per second. That's 20,000 kilogram meters per second of momentum. And its final momentum, if it's stopping, its velocity is now 0, which means its momentum is 0. So 0 final minus initial 20,000 gets you a change in momentum of negative 20,000 kilogram meters per second. Now, what does that mean? Change in momentum. Calculating change in momentum, what is that? Why is that a big deal? Well, change in momentum is impulse. So J is change in momentum. It's impulse. Now you'll see some equations in this discussion with multiple equal signs. Okay. All this means is this is all the same. You could pick any two parts here, and that makes an equation because they're all equal. Okay. Now, since impulse is just a change in momentum, it gets the same units as momentum, kilogram meters per second. Okay. So a car is initially parked and it accelerates to 15 meters per second. What is its change in momentum? Where did it start at? What was its velocity when it started? 0. So its momentum to start is 0. Okay. Final momentum is 1,000 times 15, 15,000. So 15,000 minus 0 is 15,000 kilogram meters per second. And if you know the change of momentum, it is the impulse. It's the same exact thing. Same exact thing. Okay. Now, before you see this example, we're talking about a ball falling and hitting the ground. This might be a preview of an upcoming project. Yeah. Things falling, hitting the ground. Impulse is going to be a key concept with an upcoming project that you're going to get some information about real soon. So pay attention. If you understand impulse, you might do okay on this project. So, a 500-gram ball of clay falling at negative 2 meters per second when it strikes the ground and sticks to the ground without bouncing. What is the impulse during the collision? Watch out for signs. So, let's walk through this. Change in momentum. Final minus initial. Final minus initial. Final momentum is 0. It hits and sticks. Hits and sticks to the ground. 0 momentum. Initial momentum is half a kilogram because it's 500 grams. That's 0.5 kilograms times negative 2 meters per second. Okay? Keep in mind, because 0 minus a negative means you're going to end up with plus 1 kilogram meters per second. Okay? If you plug in your calculator, you see what I mean? It's basics. Okay? If we found something that bounced, okay, like a bouncy ball, and dropped it, same mass, 500 grams, and bounced it, do you think that a bouncy ball will have a greater impulse than the sticky clay? So hit and stick, 1 kilogram meters per second. Bouncing, what do you think? Take a second, see if you can calculate on your own. Maybe pause the video. See if you think you can calculate the impulse. Because I'll tell you, because it bounces, it's actually going to have a greater impulse. Greater impulse because it reverses direction. So if we calculate it, final momentum is half a kilogram times 2 minus half a kilogram times negative 2, because that was going down to start. So you get 1 kilogram minus negative 1 kilogram. That's the same as plus 1. Ends up with 2 kilograms, literally twice as much impulse, twice as great of an impulse. Okay? Now notice we haven't talked about how long it takes for something to change momentums. Impulse by itself does not necessarily care about time. In fact, there are lots of ways to deliver the same impulse. You could have something slowing down a little, something slowing down quickly, and then slamming into a wall. Believe it or not, all of these result in the same exact impulse on this object. The same exact impulse. Because the final velocity and the initial velocity and the mass are all the same. So you get the same impulse. But what's the difference in each case? Think about if you were in this car, coming slowly to a stop. It's a gentle stop. Slamming on the brakes, you kind of jerk forward a little bit. Hitting a brick wall, you might go through the window. We think about the concept of force of impact is different for these different examples, okay? Sorry, I had to edit this into 2 parts, but we just said how the force of impact is different for the different examples, okay? So there has to be a way to establish that mathematically, the different amount of force of impact. Now, and think about what's different for each of these examples. Besides just the force of impact, what else is changing? The amount of time it takes to change impulse is also changing. Okay, so for example, in this first example here, the amount of time is quite large. Whereas hitting the brick wall, the amount of time is incredibly small. So what happens to force of impact as the time gets smaller? Well, as time gets smaller, force of impact goes up. The same can be true about the other way. So if you increase time, then the force of impact goes down. And this is represented through another version of the impulse equation. Okay, so we said that impulse equals change in momentum. This is another one with 2 equal signs, which means all of this is all equal. Okay, if you were doing a problem, you could just pick out 2 pieces of these 3 and work a problem like that. The new part is this middle one. F delta t. Remember, delta means change in time. Force times change in time. Specifically, we're talking about this force of impact. Think about it like that. Force of impact, okay? A force exerted for time delta t turns into an impulse, okay? So force times change in time. If impulse remains the same, force and time have what's called an inverse relationship, meaning when one goes up, the other goes down. So if you increase time of impact, force of impact goes down, whereas the opposite is also true, okay? This would relate to cars. Think about this, cars crashing. Modern cars are designed to crumble. That's why accidents look so bad on the highway. When a car crumbles, the amount of time of impact goes up. However long a car company can extend this crumbling phase, the amount of time goes up, which means force of impact exerted on the person in the car goes down. In a NASCAR car, the actual roll cage where the person sits in the middle is designed to disengage essentially. The front end and the back end of the car fall apart, all designed to increase the time of impact and reduce the force of impact. Okay. So this also gives us another unit of impulse because you have newtons and seconds. A newton second is the same as a kilogram meters per second. You're probably going to see us use kilogram meters per second for impulse forever. We won't really be using Newton seconds very much, but they're the same exact thing. They actually mean literally the same thing. All right. So impulse is also a vector. It has a direction. It can be positive or negative. The direction of the impulse is what the positive and negative are representing. Okay, let's do an example. Jonathan applies his brakes for 0.5 seconds, which imparts an impulse of 1,000 Newton seconds. Okay, what force did the brakes apply to slow down the car? Force. Okay, let's look. So, an impulse of negative 1,000, time is 0.5 seconds. So if you know your time, to get force by itself, we would divide by time. So we divide negative 1,000 by 0.5 and get negative 2,000 newtons of force, okay? A negative force gives a negative impulse, okay? If you have your digital textbook, you can actually find this equation and you can use the run button here to actually see what that would look like on a car, okay? So, applying what you've learned. To change an object's momentum, a large force or short time, or small force in a long time. So if you were trying to protect, say, an egg in a future project, this is where impulse really applies a lot. It's the idea of finding a way to increase the time of impact to reduce the force of impact. And by time of impact, I literally mean the time from when something first touches the ground to when it stops moving. We're not talking about 10 seconds. We're not talking about 5 seconds. We're talking about like half a second, tiny amount of time. Okay? Think about how long it takes for a car to stop vibrating once it's been hit. Okay? It's a small amount of time. Okay? So anyways, helmets, padding, that they all do the exact same thing. They do the exact same concept. That's how sports pads work, like helmet pads. They increase the time of impact to reduce injuries and things of that nature. Okay, if you didn't know that's how that works, well, there you go. Same thing with airbags. Airbags, that's the whole concept behind airbags, is that you are adding a cushion, a pillow essentially, and you're trying to increase how long that person's head pushes against the airbag and pushes back, okay? So as it squeezes the airbag and gets pushed back, that's an increase in time. Calculate the change in momentum of a 1,000 kilogram car that speeds up from 10 to 15 meters per second. Remember, change in momentum, final minus initial. So you have a final velocity of 15. Momentum is mass times velocity. So take a second, see if you can solve this. Maybe pause the video if you're working. Give yourself a chance to try to work this out. Because basically what you should have gotten is 1,000 times 15 minus 1,000 times 10. So 15,000 kilogram meters per second minus 10,000 kilogram meters per second equals 5,000 kilogram meters per second. Which set of units below is not impulse? Well, you should know this one. We've talked about, we've used kilogram meters per second and we've used Newton seconds, but we have not used kilogram meters squared per second. A 2 kilogram rocket is subjected to a constant force of 400 newtons that accelerates it from rest to a speed of 100 meters per second. What is the impulse applied to the rocket? How long did this event last? So we have to use a couple of our impulse equations here. Impulse applied, 2 kilogram rocket, 400 newtons, accelerates from rest. Rest, how fast is that? 0. Final velocity is 100. Initial is 0. Okay, so to find the initial impulse, it's going to be final minus initial. So final is 2 times 100, 200 minus 0, 200. How long did it last? Well, now we know the impulse. An impulse equals force times change in time. Well, we know the force, 400. So you can set it up as impulse equals force times change in time. Impulse is 200. 200 equals 400 times time. To get time by itself, you divide by 400. It looks something like this. Okay, divide by 400. 200 divided by 400, half a second. All right. So that's where we're going to leave you off here today with our notes. We have a worksheet coming up, but hopefully you've learned a little bit about momentum and impulse. Y'all have a great day. Thank you.